Okay, hi again. I'm going to talk about kernel-based bandits, fundamentals, and recent advances of this problem. Kernel-based models are very elegant technique to extend linear models to very general nonlinear ones with great representation capacity. One example that has gained particular interest in recent years is the infinitely wide neural network, which as shown in this paper can be modeled as a kernel. And this problem in general finds applications in a variety of domains, including parameter tuning for robotics, neural networks, molecular design application, recommender systems, sensor networks. But in general, in this kind of problems, we have not very large number of parameters where we want to regress or optimize performance over these parameters. So just an overview of what I'm going to cover today. I'm going to talk about kernel-based models first to overview what we mean by kernel-based model, then talk particularly about kernel-based bandit optimization. As this is a theory seminar, I'm going to cover a little bit of the analysis of a popular algorithm UCB policy, which you may be familiar with, to just give a sense of why analytically these kind of models work. And then just cover a little bit about the recent advances on the problem in recent years, last couple of years, some open problems, as well as some emerging research directions, which are gaining interest. This is completely interactive. Feel free to stop, ask questions. If something is unclear, please let me know. So do not hesitate to interrupt if you have any questions. So first, overview of kernel-based models. So what's a kernel-based model? Provided a data set, which is a collection of input-output observations, and a kernel, so assume this kernel is given, which is a function from the input space times input space to R. The kernel-based models provide us with closed form prediction and uncertainty estimate. So the prediction is, this is the formula for prediction. In these notations, K, X, and Xn is the so-called kernel matrix or the covariance matrix, which is a joint application of the kernel to input points. And K, X, and dot is a kernel vector, which is the application of kernel to the observation point and the point of interest, the point that we are looking for the prediction at that point. If you're not familiar with these formulas, don't worry. These are simply the conditional mean and covariance of multivariate Gaussians. So basically, if you look up conditional multivariate Gaussian, for example, from Wikipedia page, you pretty much see formulas which are kind of resembling these two formulas. But I will try to give intuition into how this could be useful and where this come from in the next slide. But for now, I just like the takeaway from this slide is that we have nice closed form expressions for prediction and uncertainty in a regression model, given a data set and given a kernel. So here is an example. So this is a true data generating function. The blue function is a true function, which we want to use data to regress. So let's say we have a one data point here. So this changes the space of likely function. So this dotted black line, this dashed black line is the regression provided by the model. And this gray area is the uncertainty that the model is predicting for this regression of this blue line. And we can keep collecting more data points. And as we are collecting more data points, basically we can apply our formulas to get better regression, like a better estimation of the blue line through this dashed black line, and a smaller and smaller uncertainty regions. So this is basically how those formulas are useful. So we can use them provided a set of data points, these cross red points, and a given kernel to provide prediction and uncertainty regions for a regression problem. So basically this provides an upper and lower confidence bounds for the true underlying function. What is the interpretation of this machinery? So one very popular interpretation is Bayesian interpretation or Gaussian process models, where noise is also assumed to be Gaussian with the parameter from those formula with this variance tau square. And the interpretation is that we have a prior Gaussian process distribution over the function. So we assume the space of the function has a prior Gaussian process. And then we use the data points, these dotted red points in the figure on the right, and Bayes rule to basically update our belief about the function. So basically, our belief about the function condition on the data, we can use the Bayes rule to create a distribution for the space of the function condition on the data, which here the prediction is the mean of the distribution, and the uncertainty region is the basically plus minus standard deviation of this Gaussian distribution. So basically, this is a maximum likelihood estimate of the true function in a Bayesian, with a Bayesian interpretation. There's also another interpretation for the same formulas and the same machinery. So exact like same formulas, exact same calculation that is referred to as Kernel-Based regression. That is equivalent to a regularized least square estimator. So here the regression that we find for the true function is a function from a certain space, that minimizes the least square error. And it is regularized by the norm of the function within that space. This space is a bit of a complex notion if you have not seen before. So this space is called the reproducing kernel Hilbert space that has a one-to-one relation with the kernel. So the kernel uniquely determines this space HK. And if we want to have a grasp of what that space is, we need to look into Mercer's representation theorem, which defines this space HK that is uniquely determined by the kernel K as the span of functions, linear span of functions in infinite dimensional basis. So we have this infinite dimensional basis with lambda m being eigenvalue, phi m being the eigenfunction or eigenbasis, and then H is the space of all function, which we can write as a infinite dimensional linear combination of this basis. And the norm of F is simply the L2 norm of the weights that determines this particular function. So from this interpretation, we can see why kernel-based models are a generalization of linear models. So it's basically the infinite dimensional linear model in the feature space determined by the kernel. So overall, it's non-linear, but it's linear in the feature space of the kernel, which is uniquely determined by the kernel. But I just want to emphasize that these two interpretations are the same. So they result in the same regression, although they are coming kind of from different backgrounds, different terminologies, they end up in the same way of computing the regression problem. You're probably familiar with the equivalence between regularized least square estimator in linear models and when we assume a Gaussian weights and Gaussian noise and do maximum likelihood estimate in the linear models. So that is a special case of this when the kernel is a linear kernel. Okay, so this is pretty much the overview of the kernel-based models. But again, like the takeaway is the first slide that we have closed form expressions for regression and uncertainty region, provided a data set and a kernel. But now let's move on to our particular problem, kernel-based bandit optimization. First, I want to just point out that you might have seen this problem with other names. So the terminology that people use in the literature has been quite diverse, partly because people who show interest in this problem kind of are coming from various communities. So it's called GP Bandit, Gaussian process bandit, kernelized bandit instead of kernel-based bandit, continuum armed bandit, because as we will see, the action space is going to be continuous. There's then going to be infinite number of actions. Some people, mostly machine learning, refer to this as Bayesian optimization because it's a way of optimization where we use a Bayesian model. Some people call it zeros order optimization in contrast to first order optimization. So first order optimization refers to an optimization where we use first order information, in other words, the gradient. But here we want to optimize a function. We want to find the optimum point of a function without having access to gradient. So that's the motivation behind zeros order optimization. And some people just call it black box optimization, again, because a function is given, we just do some process to see one value of the function and try to use this to find the optimum value for the function. Okay, but let's look at the mathematical formulation of the problem. So what is kernel-based bandit optimization? So consider the sequential optimization of a function f. So simply a function f from a certain domain to R is given, and we have access to a sequence of n noisy observations, which we can actually determine which point we want to observe. So we have access to this n noisy observations like xi, yi, I from 1 to n, where yi is a noisy evaluation of f of xi up to this basically epsilon I noise. Let's use this notation x star for the optimum point of f, which we use argmax, but it could be argmean. Different papers prefer different ways of presenting it, but I think we can just go with argmax and everything translates to argmean as well, simply. So let's say this x star is one global optimum point of f. So our objective is to design the sequential points in a way to get as close as possible to f(x) star. Like for example, this could be rewards in a reinforcement learning problem. This could be performance of a particular design in an industrial design problem, or it could be the performance of a drug in a clinical trial problem. So it's kind of a very general mathematical formulation of optimization problem where we have access to the observation values of the function. Just notice that a very naive way of solving this problem is to just collect a large number of discrete samples and choose the best among those discrete samples. But that could very quickly become inefficient when the dimension of the input grows. So for example, if you want to have a discretization that is as fine as having 10 points along each coordinate, and we have 10 parameters, like 10 dimensions, that will become 10 to 10. So we have to collect 10 to 10 samples, which could be very large for some applications, for example, industrial design, clinical trial, or hyperparameter tuning, as I said. So we want to basically find the efficient and kind of judicious way of selecting these observation points. Here, the goal is to reduce the number of samples, take as few samples as possible. So in figures, this is basically what we are doing. For a simple function from R to R, this x star is the optimum point. So our goal is to converge to this x star. We start from x1, we see an observation, we decide to take another observation, x2, and then based on this, we decide to take another observation, x3, and based on this, we decide to take another observation, x4, and our goal is to select these points in a way that it converges to, it gets closer and closer to this x star. The performance is typically measured in terms of cumulative regret, coming from reinforcement learning literature. That is the total loss in the function values at the observation points compared to the optimum point, compared to the maximum point. Or sometimes it's people just use simple regret, where in the simple regret terminology, usually we just compare the loss at the end of time horizon. So we take n samples at the end of time horizon with n samples. We select, basically the algorithm outputs one candidate for the maximizer, and we see the difference between the true maximizer and the maximizer that the algorithm is predicting. Which performance measure to use kind of depends on the application. Sometimes we are interested in this, sometimes we are interested in this. Depends kind of on what, how we define our problem. So for example, in reinforcement learning, people usually use this because each action matters. But in some applications, for example, in hyperparameter tuning, we could use this because what really matters at the end is the set of parameters that we select at the end for our model. Okay, so let's look at some classic algorithm to solve this problem. So how do we solve this problem? One very popular algorithm is the UCB algorithm, where we use our model, which here is a kernel-based model, a kernel model, to create the prediction and uncertainty regions, and then select our observation point, our next action, as the point that maximizes our upper confidence bound. So basically, on the figure, in the figure on the left, we have this blue line that is the regression, and these blue areas that are the uncertainty regions. In the middle figure, we're explaining UCB, where we select the next observation point based on the upper confidence bound. So we create an upper confidence bound based on our model and simply set xn as the point that maximizes the upper confidence bound. Another popular algorithm is Thompson sampling, where we just sample from the belief. So we don't know the true blue line, right? But we can sample from our current belief and create this green line, and then choose the point that maximizes our sample. So these are, I would say, two of the most popular classic algorithms for Bandit type of problems. So I will focus on UCB and say a little bit about the analysis of UCB and why this works. If there is interest, we can have another talk where we cover Thompson sampling as well. But the analysis is a bit more complicated, and in the favor of time, I'll just focus on a UCB algorithm. So the UCB algorithm is also sometimes referred to as optimistic optimization in the literature. And the reason for that is basically what we're doing here. We're saying we don't know the true function to choose its maximum. We have a belief. We select the points based on their best statistically likely performance. So this is basically the orange line at the top of the figure in the middle figure, and the graph in the middle figure is this orange line, is what is the best kind of we expect from this action to give us. So because we are being quite optimistic about judging the actions, so sometimes the UCB algorithm is also called optimistic optimization, or in reinforcement learning, also people use the term optimistic often to refer to UCB kind of algorithms. So what I want to cover next is the kind of like a bit of theoretical analysis of UCB. And then I will move on to some basically pointers to recent advances and some open problems. Is there any question up to this point?
Hi, Satar.
Hello.
Hi. Okay. I have a simple question. So in practice, how do people compute these argmax either in UCB or Thompson sampling? Because for example, in your example, in your figures, this corresponds to maximizing a non-convex function.
Okay, that's a very good question. Actually, I think that's also a quite important question. So yeah, so it seems that we are in a loop. We are kind of turning non-convex optimization to another non-convex optimization. So we want to optimize an F, which we don't know, to optimizing the upper confidence point to select the observation point. So yeah, exactly. So the justification or reasoning that there is in the literature to basically motivate this approach is that selecting a point from F or observing F is much more costly than selecting a point or observing the UCB. So in some cases, for example, in industrial design, selecting a point from F amounts to having a design of parameters, running a system, and seeing the performance, which could have high monetary or time cost. While optimizing the UCB is a purely computational thing, so it depends on the computational resources at hand. So basically, the costs are from different natures, and this is justified for the cases where observations from F are much costlier than the observation from UCB.
I understand this perspective. What I'm curious about is that typically, although we already have some provably convergent algorithms for non-convex optimization, but typically this requires some assumptions on the function to be minimized, and it turns out that in UCB or Thompson sampling, the resulting function we want to maximize can be quite arbitrary. And therefore, it becomes difficult to verify these existing assumptions for convergence of non-convex optimization algorithms.
I see. Yeah, no, I agree. Completely agree. So there are a few ideas here. So one is to just discretize the domain with a progressively fine discretization. So then we can basically account for the effect of discretization and the convergence and see what is the best size of discretization. But that would still require exponential in the domain large number of discretization, right?
Yeah.
So, but that's one basically mostly like academic theoretical approach. In practice, we can just use an off-the-shelf optimizer, just like, like input it to Python, use an off-the-shelf optimizer like BFGS, but that doesn't come with a strong theoretical guarantee if xn that we have chosen is really like the best point in the UCB. But in practice, that works well. So it seems it's not really important that we select exactly like the optimum point. It's still like we're guiding the algorithm in the right direction because this is a point that has higher value compared to other points. But it's difficult to recreate the regret points with such kind of approximations.
Okay, I see. Thanks.
And for Thompson sampling, there are some more actually I would say rigorous approaches using variational methods to create simpler functions to track, which are kind of like closer to the original function, and we can sample from those easier. but that's a bit more involved. For example, if you can write these functions in the basis, in a certain basis, we can truncate the basis and use,
but this approach is essentially approximate.
Exactly. So then we can use variational model to create an approximation of the sample, which we can sample efficiently.
Okay.
Which we can find the maximum efficiency too. Yeah, but I agree. This is a very important question, and actually, I think that this is one of the spaces where there is a space for research on how to implement these algorithms in a way that is both efficient and the proofs basically go through.
My feel is that this requires some new idea. Currently, both UCB and Thompson sampling basically only focuses on the statistical part and not on the optimization computational part. I think to have a rigorous scheme requires a consideration in both the statistical and the computational perspective.
Yeah, I completely agree. I completely agree that also I am more focusing on sample complexity rather than computational complexity. And I think there is a great room for research on the computational complexity.
Okay, thanks.
Yeah, thanks for the question. Okay, moving to the analysis of UCB. So I'm going to give a very concise and simplified version of the analysis. There are more details, but I will point to references to look into a more detailed analysis if you are interested. But my goal is here to help you to, if you haven't seen this before, and if you see this slides, I hope when you go into that paper, those papers, and look at the more complicated analysis, you can just follow it easily. You say, okay, this is this step, this was this step. Just like give you a general intuition about what is going on in the analysis and why this is working, which is quite simple. I think the main message is quite simple. So, as we said, the kernel-based model gives us confidence bounds. In terms of a regression, so this mu nx, the posterior mean of the GP model or the regression of kernel ridge regression, plus minus some coefficients, beta n, which I'll come back to this, multiplied by the standard deviation. So it's basically like saying the value of a Gaussian is most likely within mean plus minus 3 standard deviation, something like that. So if you recall, like these figures from earlier in this presentation, so we have these blue functions which we want to estimate. We have this dashed black line, which is the prediction, plus minus a coefficient of the standard deviation gives us a confidence region, which with high probability, we know that F is within these two. But let's see what is this confidence interval, what's multiplier beta, and what it depends on. So this is one result that establishes beta and delta as this formula. So this log 1 over delta is kind of expected when we expect the probability of 1 minus delta. This is something like Chernoff-Hofting inequality. Those kind of inequalities typically depend on these kind of terms. And this R is the parameter of the noise. So we need to make some assumption on the noise. For example, make the assumption that the noise is sub-Gaussian. That's the assumption in this formulation they make. But this is not very limiting. We can extend this to light tail noise or even heavy tail noise, but the shape would slightly differ. But the two other terms which are new here. So one is this B and one is this gamma n minus 1. So this gamma n kind of captures the function class complexity, which is determined by the kernel. So what kind of functions we are talking about, what complexity these functions have. And the parameter B, which is the normal function within that function class, within that space of functions, which is the norm of the function, basically determines how complex the function is within the function class, because within the function class, we could also have different levels of complexity. To give an example, for example, if we're talking about linear model, then the function class complexity is the degree of the space, sorry, the dimension of the space, so D, the dimension of the space. And the complexity of the function within function class is the norm of the weights of the function in the linear model. So basically, these are kind of determine how complex the model is, and then we can create these confidence intervals. But there is a subtle consideration here about this beta, which I want to emphasize. And it is that this formula which we have in the bottom, which is very popular from this paper by Chaudhuri and Gopalan in 2017, also another paper which is initially on linear bandits, but extends this to kernel-based bandits. This is under the assumption that xn are selected adaptively. So each new observation point depends on the past observation, which is the case in Bandit and reinforcement learning problem. So there is a notion of adaptivity in the way that we collect observations. So this is different from the just classic typical regression problem, where we have a collection of data points and we use them for regression. So here we are selecting the observation points adaptively to basically reach a certain objective, a certain goal. And this adaptivity creates additional statistical complexity, which needs to be handled, and it gets us to this particular beta at the bottom. But if you consider non-adaptive samples, where xn are chosen independent of the observations, and notice that the observation is made of a deterministic function, so there is not much information in it, and noise, right? So basically what we care about is basically if the observation points are chosen depending on the previous observation, which means if they are chosen depending on the previous noise or not. So if they depend, we have this more complex, larger confidence interval based multiplier, which depends on the complexity of the function class. But if they don't, then we have a simpler confidence interval based multiplier, which is pretty much the same thing except this gamma, the function class complexity. But this subtle difference actually becomes quite important in the regret analysis, as we will see later. I will show you why this is very important. Okay, so let's go back to analysis of UCB. So I'm kind of taking the main points from this paper, which is a recipient of ICML 2020 Test of Time Award, which is an award that ICML gives to an impactful paper from 10 years ago. And so this paper is the first paper that gave a finite time analysis for kernel-based UCB. So just to recap how it works, we select the next observation points as the point that maximizes the upper confidence bound created by the kernel-based model. I'm not specifying this beta n because there are little things to be considered regarding the union bound over time and over x. But let's say it's just this is a confidence interval that holds. Let's say this is an upper confidence bound to make the analysis a bit simpler. So then what we have for regret at sample n, so the loss at sample n, fx star the maximum minus fxn, we can upper bound this by the upper bound on fx star. So instead of fx star, I just set the upper bound on, I just write the upper bound on fx star. And instead of the lower bound on fxn, I just write, instead of fxn, I just write a lower bound on fxn. So these are the upper bound and lower bound that our kernel-based model gives for fx star and fxn. Basically quite simple. The first step is quite simple. And the second step is the magic of UCB. So in the second step, we know that we have selected xn. So this is where UCB algorithm becomes important and effective. So we know that we have selected xn in a way that the upper confidence bound for xn is larger than any other point, right? by definition, exactly by definition, how we choose xn. So xn is selected in a way that the upper confidence band is large at xn, larger than any other point. So then we can write the upper confidence band at x star is upper bounded by the upper confidence band at xn. So this comes from the definition of UCB, and then becomes simple. We just cancel out these two terms, and what we are left with is 2 times confidence interval West multiplier multiplied by the standard deviation. Okay, so in this way, we bound the regret at time n by the standard deviation at xn. So to upper bound the regret in general, we just sum up over n from 1 to capital N to the time horizon. So this beta n in nature is increasing, so I just replace all beta n's with beta capital N, summation of standard deviation. So basically our regret is bounded by beta n multiplied by summation of conditional standard deviation, so standard deviation for this sequential set of points at the observation points. Okay, the second piece, the other piece that completes the analysis of the UCB, which is shown in this paper by Srinivas et al. In 2010, is that the summation of conditional variances, so variance at each point conditional on all the previous observations, is upper bounded by gamma n, which is the same gamma n. So basically the complexity of the function class. So from here to here, we use the Cauchy-Schwarz inequality, replacing bounding the summation of a standard deviation with a square root n summation of variances. So we get to this upper bound on regret. So basically the first piece is just some simple steps using the UCB definition to prove that the regret is bounded by a standard deviation. The second step is to bound the total standard deviation using a bound on the total variances based on the complexity of the function class. Now, if you remember this beta n for the confidence interval Betz multiplier, for adaptive samples was growing with a square root gamma n. So the dependency on gamma n was a square root gamma n. So if we replace that dependency for beta n square root gamma n, we have also 1 square root gamma n under the square root. So we get a regret of gamma n square root n. So our regret is determined by the complexity of the function class multiplied by a square root n. So now let's take a closer look at this regret time and see how good it is. So in order to understand this, let's try to understand gamma n a bit better. So the first line is just a mathematical definition. So one way to define the complexity of the function class is the largest value that log determinant of the covariance matrix can take. So basically just log determinant of the covariance matrix. But intuitively, to understand what is this happening, I'm going to basically explain it in a different way. So gamma n can also be explained in this way. So in a kernel-based model, as I said, we have a linear model in the infinite dimensional feature space uniquely determined by the kernel. But for a finite data, not all the features are going to be important because we have a finite data. So only a finite number of data, only a finite number of features can have a significant effect. This is very intuitive, very hand-wavy. I'm not being mathematically precise, but just the point is there is going to be an effective dimension of this infinite dimensional feature space for a finite amount of data. And this effective dimension is basically gamma n up to logarithmic factor. So basically gamma n up to logarithmic factors determines the effective dimension of the model in the feature space of the kernel. It also can be mathematically just defined as the log determinant of the covariance matrix, which for people familiar with information theory this is just basically the mutual information between the observations and the latent model. So basically different interpretations. I'm not going to go into the details of gamma n, but I will share papers that you can look into it, which are written specifically on gamma n. It's kind of like a bit tangent to the topic. But yeah, I just want to kind of mention what do we mean by complexity. But what are the exact values for gamma n for different kernels? For example, if you have a linear kernel, this gamma n is basically the dimension of the input up to logarithmic factors. For very smooth kernels, a squared exponential kernel, which can regress very smooth functions, infinitely differentiable functions, gamma n is logarithmic in n. But for kernels with basically more powerful representation capacity, we can represent rougher functions, which are not infinite times differentiable. Then the gamma n is polynomial in n, where the exponent depends on the smoothness of the function. Basically, how the smoothness functions are is captured in this formula, and it's polynomial where the exponent depends on the smoothness of the function class. But the reason I'm mentioning this is that this regret bound shown for classic algorithms such as UCB and Thompson sampling is not always sublinear, because gamma n can grow faster than square root n. So gamma n can take any value between a constant for finite dimensional domains to basically n. So it could grow faster than square root n as we are making the model more complex. And that will give us a superlinear regret bound, which is trivial, because linear regret bound trivially holds. But still, this is a quite a strong result. As I said, the paper is celebrated. If this is clear, now I'm going to just move on to a bit more recent result, including how to address this issue with the regret bound. But if you have any question up to here, please feel free to ask. Okay. So recent advances, open problems, and emerging research direction. So here I'm just going to mostly just give pointers, hint at the papers and what they're doing. But I have a full list of papers at the end of this presentation. So I will share the slides and you can take a deeper look into basically any of the papers which resonates with you, you find interesting. Okay. So one algorithm that addresses this suboptimal regret bound issue is this batch pure exploration, which is a ASTAS 2022 paper, which solves this issue and shows a regret bound that is order of square root gamma n. So this regret bound is always sublinear. It solves the issue with the regret bound. Their algorithm proceeds in batches of observation. So they divide the time horizon n to m batches of observation and use the confidence intervals based on non-adaptive observations within each batch to remove the suboptimal arms at the end of each batch. So basically, the idea is to design an algorithm that is capable of using non-adaptive observations. And they just select the batch size in a way that they give us this, it gives us this regret bound. And we know that this is optimal because it matches the lower bound proven in this paper. So just to see mathematically what they're doing, within each batch, within the ith batch, they just select the next observation point as the point that maximizes the variance. So they don't want to converge, it seems like they don't want to converge to the optimum point. They just try to reduce the uncertainty. But at the end of each batch, we use confidence intervals to basically prune the space and just limit the space to the arms or to the regions which can be the maximum. But here, because of the non-adaptive nature of the samples within each batch, we can use confidence bounds for non-adaptive samples, which doesn't have that additional gamma complexity term. So this allows them to prove this order optimal regret bound. So it's a 2022 ASAS paper. I recommend it very much because it also has a very nice literature review, explains the problem and puts the problem in the context. There are a couple of a few other works very recently kind of developed in parallel. The relationship between them is not really discussed very well in the literature, but these two papers, 2021 papers, also show the optimal regret bounds for more complex algorithms than the algorithm that I just explained. There is also this paper from 2013, which has very interesting discussions on the optimal regret bound. So I also recommend taking a look at this paper if you're interested in this problem. But this leaves us with an open problem. So we still don't know if the suboptimal regret bound for classic algorithms such as UCB is a fundamental limitation or an artifact of the proof. So basically, we have algorithms that give us the order optimal regret bound, but we don't know what is happening with UCB is really like a limitation, or we just cannot prove a better regret bound for it. So I think this problem can be solved by either showing a lower bound for UCB, like finding a difficult function, particularly difficult function, on which UCB cannot achieve sublinear regret, and proving that, or just fixing the proof of UCB to show sublinear regret with UCB. So yeah, a formalization of this problem can be found in this paper with more details. Another interesting problem, which probably has more academic value, is what is the best achievable regret for the noise-free setting? And this is also another very interesting problem. So this paper, 2011 paper, drives regret bounds for simple regret in the noise-free setting. But we still don't know what is the best we can do in the noise-free setting. But by noise-free, I mean let's say we have sub-Gaussian noise and we set the parameter to 0. So basically, there's no observation. For each point that we select, we see the exact function value. What is the best regret performance that we can have? So one way is to just set R equals 0 in the results that we have for the noisy setting. But that seems to result in loose regret bounds for the noise-free setting. We probably hope to get tighter regret bounds for the noise-free setting rather than direct application of the results in the noisy setting. But basically, the question is, consider the problem formulation in this paper, which drives the regret bounds for the simple regret in the noise-free setting. Can we do similar derivation for cumulative regret? So these are, I think, two of the interesting open problems related to the analysis of kernel-based bandits. Here, I'm just going to give a few pointers to some interesting papers if you're interested to do research in this area. So I think one interesting research direction is to look into more complex domains. So what we said so far is kind of assuming that the input domain is RD. So we have functions from RD to RD. But the kernel-based models are very powerful and can cover other input structures, including, for example, graphs or arbitrary manifolds. So these two papers written by same people give some very interesting intuition into how to define kernel-based models and apply them to more complex structures. I think there might be some room for research to basically solve problems over this complex domain. For example, this figure in the top shows an application that they considered their paper for kernel-based models in social networks, which I find very interesting. And also, I think this paper won the best student paper award at AStats 2021. So I totally recommend both papers. I think they're very interesting papers. Okay, another research direction which has already people started to work on, is gaining more interest, is using these kernel-based models to create an upper confidence bound for Q function and providing analysis for RL problem, for the regret ones in the reinforcement learning problem. These three papers, I think, are quite interesting. They kind of like give the main ideas, but there is still like quite a lot of details to be figured out for these problems. It's a relatively new problem with very recent papers. Okay, another interesting research direction I would say is overparameterized neural networks. So as we said, the infinitely wide neural networks are equivalent to a kernel-based model. And there are also some work on the error between finite and infinite neural nets. I find this a very good example, but I'm not really familiar with this literature. Maybe there are better examples of papers working on this. And there is a series of papers basically combining these two types of results to derive bounds on optimization problems on neural networks, which they call neural bandits. So basically, they take a neural network, which is overparameterized and not necessarily infinitely wide. Then they use a kernel model for the infinitely wide neural network, and they bound the error between the finite and infinite neural network to basically drive results for a neural bandit problem. So one of these two papers, I think the 2020 paper considers neural UCB, so it's the application of UCB data collection to neural network. The 2021 paper considers Thompson sampling, and this other 2021 paper is actually this Castro and Krause 2021 is actually published in AStats 2022. So these are also, I think, generally interesting problems, and I think there's a lot of room for research in this area too. And okay, the other thing is the computational efficiency, but from a different perspective than the question that Professor Lee asked earlier. So it's not about like optimizing the UCB or the Thompson sampling, basically sample, but on the computational efficiency of the closed form formulas themselves. So recall that for the prediction and uncertainty estimate, we had these closed form formulas, which have order of n cube computation because of this matrix inversion. But there are other methods, such as Bayesian variational methods or Nystrom method, which help us to basically do these computations faster, as fast as order of n in some cases. And we also have a recent paper on arXiv, kind of dealing with this problem and drawing some connections between the both methods, Bayesian method and Nystrom method. I would also recommend this paper. There may be some inspiration in these papers on basically finding more computationally efficient algorithms for kernel-based bandit. Yeah, this is pretty much all what I want to cover. So summary, we just had an overview of kernel-based models. We talked about kernel-based bandit optimization in particular. What is the problem? We went a bit deeper into the analysis of one of the algorithms, UCB, and then we just talked about recent advances, some important open problems in the literature. For some of the suggestions for research directions, I just mentioned complex domain, computational efficiency, episodic reinforcement learning, and neural bandits. I know it was a bit quick, and I just basically named a few papers, but these are the papers that I found important, and I have a full list of papers at the end of the slides. I will share these slides, and if basically any topic, any question sounds interesting to you, you can look into those papers. So if there are any questions, I'll be happy to take questions now. Can someone say something that I can just make sure that I can hear you?
We can still hear you, or I can at least still hear you.
Okay, thank you. Okay, yeah, if there are no questions, I will just share the slides with you through an email. And just remember that we have a Slack account that we can use for communication if you want to discuss something. We also have a Zotero library, which I will share the link again in an email after this meeting. For the next meeting on 12th of April, Mark will give us a presentation. Yeah. So yeah.
Yes. Thank you. Bye.
Thank you. Thanks everyone. Thanks for your time.
Thanks. Bye.
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 Thank you.